decide what to do. And nothing official has come out yet, but that's what that whole meeting was about. So the executive council is kind of like the select group of the Senate, the actual voting members. I wasn't invited to that shit, even though I'm on the executive council. They had some people from student government, they had the college president, the provost, and a few other people get together and basically argue with each other about whether we're going to wear masks. So you guys jumped in on an interesting moment in a conversation I was having with my wife about what Santa Fe is going to do in the fall regarding mask mandates. I'm like kind of in the loop on this just a little bit. It sounds like they're leaning towards indoor mask mandates for the fall. And it's a fascinating thing if you're at all interested in the politics of the college, because because masks are a bit of a pain in the ass. And there are enough people who have gotten the vaccine that are tired of wearing masks that are just grumpy, basically, that this thing hasn't gone away yet. Just wishing everybody would get the damn vaccine and mask up for a few weeks so we could put this in our past. Of course, reality is what it is, and the safe move is probably going to be to wear masks indoors, as long as there are these two new variants circulating out in the wild. I don't really know. I don't know what's going to happen. I know I'm vaccinated. I advise you all to get vaccinated, but there are good reasons to be a little careful. So we can change gears and get back into class. I think I heard someone saying something there, but I couldn't quite make it out. Is there a question?
So, I mean, I don't mind saying what the email's about, but I know you didn't see the email, didn't email it back. My dad actually passed away from COVID 2 days ago.
Oh, Jesus. I'm so sorry to say that, Ainsley. The reason I was actually just going through my email and stumbled across that conversation is I was looking for yours so I could talk to you here. I'm really sorry to hear that.
Yeah, the funeral is Monday, so I just have to figure out a different date with you for the final.
That's fine. We will figure something out. Yeah, don't stress. We can work together. I'll send the department chair an email letting her know that I have a student who needs to take the final and off time. That's certainly one of the things that that justifies moving a test date. So don't stress. We'll make it work. And I am getting through my email. The whole reason I was talking about that is because I was looking for yours. Let's get into the material for the day. Today is the 5th. And I guess if there's anything to learn from that, it's probably a lot to learn from that. But one of the things, please get vaccinated. If not for your own safety, then for the safety of the people around you who either cannot get vaccinated, or even with the vaccine, that low probability that something gets through can be quite dangerous. Today, we're going to talk about summation notation. It's going to be a short lecture. This is not an incredibly complex topic, but it's something that requires a little bit of practice because the notation is somewhat intimidating, and it involves some symbols you haven't seen before. We are going to call back on one of the things that we used last time, where we talked about geometric sequences, how if the common ratio is small, has absolute value less than 1, then as n gets larger and larger, the r to the n gets closer and closer and closer to 0. That's actually going to be important for us today in a neat fashion. But before we get there, I'm just going to show it to you. Imagine you have a sequence like, and I'll just give you an example. How about 1 over 1, 1 over 4, 1 over 9, 1 over 16, 1 over 25, 1 over 36, and so on. So you have a sequence like this, for example, and you want to add up a bunch of terms of that sequence. Like maybe here I want to add the first 4 terms. So like I want to add 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16. Sure, I could write this out. That's an option. But we've been playing around with a new notation for sequences. We know that I could describe this long list of numbers using the notation an equals, what's the pattern there? Anybody help me with the formula for the nth term of this sequence?
1 over n squared.
Very good, right? The upstairs is always 1. The downstairs is the square of 1, the square of 2, the square of 3, the square of 4. So this is an equals 1 over n squared. And here n is starting at 1, right? So n equals 1, 2, and so on. Well, often enough, mathematicians, physicists, scientists of all flavors need to add shit up for so many reasons. In physics, the way you find the net force on an object is by adding up all the forces acting on that object. In chemistry, one of the ways you can determine what's going to happen with your chemical reactions is by summing all of the little sub-reactions that go on. Analytic chem. So many other places, right? What we want to do is once you find a sort of pattern for the way something evolves, you want to add up all of those things. Well, just like when it comes to writing out big ass lists like this, we like to find a nice condensed, simple notation that encodes all of that information. If I have a big, long addition problem, I often want to express that in a form that takes up less space. So in place of something like this, I would like a notation that says add up 1 over n squared, the terms of that sequence, from n equals 1 to n equals 4, right? That's the first 4 terms. 1, 2, 3, 4 terms. 1, 2, 3, 4 terms. But here, rather than listing them, I'm adding them up. So I'd like a notation that says this. That notation exists, and it is the following. 1 over n squared, and then just to the left of that, I put a capital Greek letter sigma. The sigma is the S sound in the Greek alphabet, and it stands for the word sum, S-U-M, to add up. And then down here, you say where you want the sum to begin, and up here, you say where you want the sum to end. So instead of writing 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, I could just write sigma n from 1 to 4, 1 over n squared. This is called the sigma summation notation. And more generally, if I want to add up the terms of the sequence an, where n runs from 1 to infinity, they have to be, in order to use this notation, they do have to be consecutive terms that you're adding up. That's the only little catch. So if I want to add up, a bunch of consecutive terms from this sequence, maybe from the, say, this third term, let me say, instead of from the third, let me say from the kth term to the, say, capital Nth term. So rather than adding up from like the 4th to the 100th term, I'm just going to use the symbols K and N. This is expressed as sigma little n equals K down here, because that's where I want the sum to start, and then you put the value where you want to end over here. And then inside just goes the things you're adding up. And this would be a shorthand for the sum AK plus AK plus 1 plus AK plus 2. And it's going to go all the way out until you get to that capital Nth term. This is what the sigma summation notation is. It's just a shorthand for writing big, long sums. The very first example we looked at there only had 4 terms, so it wasn't much of a headache for me to write this out. But if I wanted to add up the first 400 terms of this sequence, all I'd have to do is change this 4 to a 400. Over here, I'd have to write out 396 more terms. Fuck that noise. Over here, I just have to change the 4 to a 400. So this is especially useful when you've got a long addition problem. I want to look at a handful of little examples just to get you comfy with it. And then I'm going to talk about a few sort of special things associated with this notation. Are there any questions just on the little introduction here, the notation we use for addition sums? Okay, so for example, maybe I want to add up from n equals 1 to 5 the sequence n squared. That is shorthand for 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is 1 plus 4 plus 9 plus 16 plus 25. And what is that? That's 5 plus 9 is 14. 14 plus 16 is 30. 30 plus 25 is 55. So if I asked you to just evaluate this sum on the left, you would write it out like this. Simplify and combine. Another kind of simple example, I could ask you to just evaluate sigma. I use a different letter here because oftentimes we use all sorts of different letters. Sigma j from 3 to 5 of 1 over j. Now you see there's nothing special about the symbol n here. I could use whatever symbol I wanted. It's what's called a dummy variable, because this is just a way of encoding the addition problem 1/3 plus 1/4 plus 1/5. Now, of course, to do this addition, you would have to have a common denominator, which would be 3 times 4 times 5. 12 times 5 is 60, and then that would be what would that be? 20 over 60 plus 15 over 60. Let's do it. 20 over 60 plus 15 over 60 plus 12 over 60. So what does that come out to? 20 plus 15 is 35 plus 12 is 47. So it'd be 47 over 60. And I will, in all likelihood, ask you to calculate some sums like this. Right? It's just one of those things. I need to make sure you guys learn this notation in this class, because it's a notation that will be used in Calc 1 and Calc 2. I think depending on what you do in Calc 3, maybe in Calc 3, some people do multivariable Taylor series, some don't. And then definitely in differential equations. I've been scaring the shit out of some differential equations students with this notation lately. this morning. Yeah. Looks scary, doesn't it? But these are the same thing. This is the exact same thing, right? This is from this morning's differential equations lecture. These are just big, big sums, right? We've got 3 capital sigmas there. So we use this stuff all the time. This could have been any day of any semester, and I would have stuff like that just sitting there. That's how we use this notation. So getting comfy just with what these say, understanding how to interpret this symbol is a big deal. A couple more examples I think are in order. And I'd like you guys to help me out with 1 or 2 of them. So for this next one, I'm going to evaluate. Again, I'll play around with the symbols. Sigma k from 5 to 10 of k. So somebody tell me, what does this mean? How do I evaluate it?
So if 5 equals k, would that be 5 till 10?
Yes, that's true. Remember, the thing that's in here is the thing that we're adding up, and we're adding it up over the values that go from here to here. So I'll just flip back to this last example. The sum from j equals 3 to 5, so you can see it. The sum from j equals 3 to 5 of 1 over j, what did we do? Well, I plugged in 3, 4, and 5 to this, right? If I plug in j equals 3, I get 1/3. If I plug in j equals 4, I get 1/4. And if I plug in j equals 5, I get 1/5. And then I added them up. So it's 1 over 3 plus 1 over 4 plus 1 over 5. So what you do is you take this thing here, you plug in all the values from here to here, and you add them up in order. So if k is equal to 5, that's where we're starting, right? I'm just going to plug in 5 for k, and then add that to what I get when I plug in the next number, and then add that to what I get when I plug in the next number, and I keep adding all those up until I get to 10. So this would be 5 plus 6 plus 7 plus 8 plus 9 plus 10. Does that make sense? So kind of this is the thing I'm adding up, and I'm adding it up over the range that's specified here. So this range is from k equals 5. You can kind of imagine that there's a little k equals 10 up here. So this says add up all of these things starting here and ending here. So this is k equals 5. This is k equals 6. This is k equals 7. K equals 8. K equals 9, and k equals 10, and then I stop here because that's the number on the top. And if you actually sum these, if you actually just do the arithmetic, you'll get 45. So this sum is equal to 45. Let's do a couple more. I think maybe the simplicity of that one makes it a little bit harder. But let's try this. Let's sum from I equals 0 to 4, 2 to the I. So what sort of things am I adding up here?
Powers of 2.
Powers of 2, right? I'm going to be adding up a bunch of powers of 2. What's the very first power of 2 in the sum?
0.
So
Like 2 to 0.
Yeah, exactly. 2 to the 0. And then what's the next term in the sum?
2 to the first.
1.
Yeah, perfect, Erica. 2 to the 1. And I'm going to keep going like this. The next would be 2 to the 2, and then 2 to the 3. And I'm going to stop when I get to 2 to the 4. That's what the 4 up here is telling me. So plus 2 to the 4. And now I want to clean this up. So let me go ahead and write out what each of these are. 2 to the 0 is 1. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and 2 to the 4 is 16. So this is 3 plus 4 is 7. 7 plus 8 is 15. 15 and 16 is 31. Okay, I'm going to give you one more like this, and then we're going to practice going the other way, going from the long form into the small form. This next one's kind of silly, but I want you to think carefully about it. Here's the sum from n equals 1 to 5 of 3. In other words, the sequence inside is the constant sequence 3. A1 is 3, A2 is 3, A3 is 3, A4 is 3, A5 is 3. So what is this sum telling me to do? Maybe someone I haven't heard from yet today.
Just add 3 4 times.
Yeah, I'm going to add 3 to itself. So when n is equal to 1, I have 3. When n is equal to 2, I have 3. When n is equal to 3, I have 3. When n is equal to 4, I have 3. And when n is equal to 5, I have 3. So if you check carefully, you'll see we'll actually have 5 of them, right? Because the n equals 1 term does give us something. So we're going to add 3 to itself 5 times, which is 3 times 5, or 15. So this is what we call a constant sum, or a sum of a constant sequence. This is the same rule. It's just if there's no n's or j's, whatever the index of summation, that's the name for the little variable down here, is the index of summation. If none of those appear in the thing inside the sigma, then that's the sum of a constant. You're just adding that thing to itself, however many times the sum specifies. Okay, any questions on these examples?
I have a question.
Sure, Bianca?
So why is in the first example different from the third example? Because I would have done the third example the same way as you did the first one.
Good question. So the big difference here is that this one doesn't have any of these things in it. But this one, this is a k, this says the summation index is k. So if this said an n, for example, and this was k equals 5 to 10, then it would be n plus n plus n plus n plus n 5 times. But this does change as k changes, right? When k is equal to 5, this thing's equal to 5. When k is equal to 6, this thing's equal to 6. When k is equal to 7, this thing's equal to 7. The number 3, on the other hand, doesn't change as n changes. When n is equal to 1, 2, 3, or 4, doesn't matter. The number 3 is just the number 3. So the thing to remember is, when you're looking inside this, the summation notation says whatever this variable is, you're going to plug in here and add all those up. But there's no variable in here. 3 is just a number. But k is a variable, right? K is a letter, and it's the same letter that we have down here. So this says plug in k equals 5. That's where you start. Then plug in k equals 6 and add those together. Then plug in k equals 7, add those together. So I think kind of a thing that Bianca's getting at here, this is how do we interpret something like sigma, let's say, k equals 3 to 7 of m? What would this mean? this is much more like this than it is the first example on the page. So kind of it's the sigma that tells you what's a variable and what's a constant. This symbol right here has underneath it a k. And the thing inside doesn't have any k's at all. So if you plug in k equals 3 to m, you just get m. If you plug in k equals 4 to m, you just get m. If you plug in k equals 5 to m, you just get m. If you plug in k equals 6 to m, you just get m. If you plug in k equals 7 to m, you just get m. This thing is a constant with respect to this sum, because this thing doesn't have any of these variables, just like here. But in the first example, this thing is not a constant with respect to this sum, because this thing has this variable in it. Is that making things better or worse, Bianca?
It makes it so much better. Thank you.
Okay, good. Now, just for fun, if we were doing this and wanted to write it somehow nicely, this would be 1, 2, 3, 4, 5 copies of m, right? So this would be 5 m. Okay. Is that right? 3, 4, 5, 6, 7. Yeah. Okay. Let's go back the other way. So let me give you some sums that are written out long form and see if you can tell me how to put them into sigma notation. I'll do a few of them here. The sort of normal thing to do is to label these with capital letters. So how about 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed? Anybody tell me how to put this into sigma notation?
So sigma from n equals 1 to 5,
Good.
and then you do n to the power 3.
Very good. Very good. That's perfect. So the things we're adding up here are cubes. 1 cube, 2 cube, 3 cube, 4 cube, 5 cube. And we're adding them up from 1 to 5. And I'd like to point out that this is the same as if I wrote sigma k equals 1 to 5 of k cubed, or L equals 1 to 5 of L cubed. That's what I mean when I say the index of summation is a dummy variable, or doesn't matter. You heard this term dummy variable a few times in the calc sequence too. All of these are just the same thing, right? It says add up the first 5 cubes. It's your choice of letter. The important thing is that the letter you're using in here matches the letter you're using down here, right? Otherwise, we run into that thing that Bianca was asking about. But most people will use n unless there's a reason not to, like you're using n for something else. So I'll use n for the rest of these. All right. S equals, how about the square root of 3 plus the square root of 4 plus the square root of 5 plus all the way out to the square root of 76 plus the square root of 77. A nice long one. Got some terms hiding in a dot, 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 but you can infer the pattern from what's there.
Sigma from n equals 3 to 77 of square root n.
Very good. So the things that we're adding up are square roots of n. And we're doing that as n runs through the consecutive integers from 3 to 77. So this is it. All right. There are some rules for sums. If I have a sum from, say, k equals 1 to n of a sum of two sequences, ak plus bk. So this would be like a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus, that's the same as taking the sum of the things individually and then adding those up. And the same is true if you change this plus to a minus. This plus changes to a minus. Nothing magic there. Another important one is that if c is a constant, and I'm adding up c times ak, then that's the same as c times the sum of the AKs. I'll call these 1 and 2, and I think it's illustrative to prove them. Learning this new notation, try to think along with me in this proof. For the first one, for both of these, I'm just going to write them out. So k equals sigma, k equals 1 to n. I'm going to do the ak plus bk1. The ak minus bk1 goes the same way. Like I said, this is the same as, or just shorthand for a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus all the way out to the very last term would be an plus bn. We all agree that this is the long form of this sum. Taken these things and just plugged in k equals 1, plugged in k equals 2, plugged in k equals 3, and so on. Added them all up, and I stopped when k was equal to n. But we know addition is associative. There's no multiplication, power is no fucky, like, order of operations things going on here. This is really just a bunch of things added up. A1 plus b1 plus a2 plus b2 plus a3 plus b. You can ignore the parentheses. And that means that you can then use commutativity to shuffle the a's together. And shuffle the b's together. And now if you look at the first string there, that can be written in sigma notation as sigma k from 1 to n of ak. And that second string can be written as sum k from 1 to n of bk. And that's precisely what we wanted to prove. Again, if you swap the plus for a minus, all of these would be minuses. And then all of the b's would just be negative. And then you'd factor the negative out. That's the proof of 1. The proof of 2 is similar. The sum from k equals 1 to n of some constant c times ak. That would be c times a1 plus c times a2 plus c times a3 all the way out to plus C times AN. From which you can factor a C, and you get A1 plus A2 plus A3 plus all the way up to AN. And now this bracketed expression is just the sum from 1 to n of AK. So that C out front comes along for the ride, and you're left with the sum from k equals 1 to n of AK, which is exactly what we wanted to prove. These two rules together have a special name. Does anybody know the term for this? An operator with these properties? It's called linearity. So over and over again, you heard me refer to linear algebra this semester. This means that sigma is a linear operator. Matrices are linear operators. Derivatives, which you will meet in your calculus class, are linear operators. What this says is if you have a sum that's made up of multiple pieces added or subtracted together inside the sum, and you know how to handle one, or you know how to handle the other, and you know how to handle them individually but not necessarily together, then you can split it up and do them one at a time. Unfortunately, there's no such rule for multiplication. You can factor out constants, but if you had AK times BK in there, you can't split that up as the sum of the AKs times the sum of the BKs. That doesn't work. All right, either my baby or my dog are snoring quite loudly. I'm not sure which one. Okay, I would like to look at one or two other little sums like this, and then I'm going to introduce you to a somewhat deep idea. I'd like to try and find a formula for the sum from k equals 1 to n, -1 to the k. So this formula, is it going to have n's or k's in it? It's a question that might take just a little bit of thinking about.
Case.
So as I work on it, I am working in terms of k. But if you think very carefully about this, what it really depends on is n. Let me show you what I mean. So I claim that this is actually a function of n. It's a special kind of function called a partial sum. If I plug in n equals 1, let me, when I plug in n equals 1, I get the sum from k equals 1 to 1 of -1 to the k. And remember what we said, we kind of sum out the k's, right? Like it's a dummy variable. I could swap it for l's and it wouldn't change anything. The sum from 1 to 1 of -1 to the k, it's just got a single term. It's -1 to the 1, which is -1. When I plug n equals 2, but we would call this thing here S1. When I plug n equals 2, that's S2, I have the sum from k equals 1 to 2 of -1 to the k. which is -1 to the 1 plus -1 to the 2. And then -1 to the 1 is -1. -1 to the 2 is +1. So that's -1 plus +1. That's 0. When n is equal to 3, I get the thing I would call S3. And that's the sum from k equals 1 to 3 of -1 to the k, which is -1 to the 1 plus -1 to the 2 plus -1 to the 3, which is -1 plus +1 plus -1. I'll write these in parentheses. So that's -1 plus 1 is 0 plus -1 is -1 again. And then when n is equal to 4, I get the object we call S4. That's the sum from k equals 1 to 4 of -1 to the k, which is -1 to the 1 plus -1 to the 2 plus -1 to the 3 plus -1 to the 4, which would be, which would be -1 plus 1 plus -1 plus 1, which is going to be 0 again, right? This is 0, this is 0, 0 plus 0 is 0. So it's the case that this object right here is a function of n. It changes as n changes. K isn't really a variable. It's an index, or it's like a space saver, right? This notation is a space saver for a sum of length n. So as n gets bigger, the sum gets bigger. As n gets smaller, the sum gets smaller. But k's all go away. I'm going to plug stuff in for k and add them up so that when I write out the sum, it doesn't have any k's, but it does always have n, right? When n is 4, the last term here is -1 of the 4. When n is 3, the last term here is -1 of the 3, and so on. So this really is, in a subtle way, in a sneaky way, a function of the letter or symbol n. And we have another name for functions of the whole number variable n, don't we? What are those called? The things we talked about yesterday. A function whose domain is natural numbers. It's a sequence. So this thing, even though it's written in terms of summation notation, defines a sequence. And that sequence is called the sequence of partial sums. Oh, sorry. Yeah. So in a very sneaky way, the object I've written down here is actually a sequence. When you plug in n equals 1, it gives you a number. When you plug in n equals 2, it gives you a number. When you plug in n equals 3, it gives you a number. When you plug in n equals 4, it gives you a number. We're going to come back to that in just a moment. But our task here was to find a formula for this thing. So what is a nice formula for S sub n? Well, when n is 1, it's -1. When n is 2, it's 0. When n is 3, it's -1. When n is 4, it's 0. It appears to be piecewise. What is the piecewise rule that Sn appears to obey? What two values is this sequence allowed to take?
-1 and 0.
1 is 0.
Yeah, perfect. -1 and 0. For what values of n will we always get -1?
Odd powers.
Good. And if n is even, we'll always get 0. So again, this apparatus, where you take a sum and then you let the upper index there be a variable, That's called a sequence of partial sums, or just partial sum. The reason we call them partial sums is because, like you may have seen on that paper I showed you from my DiffEQ class this morning, oftentimes we like to look at sums that don't stop, that go on and on and on and on and on forever. You may have seen the infinities up here at the top. The partial sum is partial in the sense that it doesn't go on forever. And this is where that geometric sequence thing we talked about yesterday is going to come back. So the last thing I am so excited to show you guys in this class is a few special infinite sums, sums that go on and on and on forever, but despite being infinite in length, have a finite value. That's a little weird. So, here we go. I'm gonna bury the lead a little bit. Or I guess I'm gonna unbury the lead. I would say your textbook buries the lead. I'm gonna unbury the lead. I want to add up the following. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus on and on and on forever. Right. I want to do that. This is an infinite sum. Or sometimes called an infinite series. And series, sometimes people just leave the word infinite off. Series usually implies infinite series in the same way that sequence usually implies infinite sequence. The trick to doing something like this, because obviously I can't do it by hand, right? If you ask me to add up the first 4 terms, I can do that. No problem. Or the first 5 terms or first 6 terms, I can do that. It might take me a minute, but I can do it. But the infinite sum, I don't have the time, right? I don't have the time. I don't have the paper. My hand is going to get sore. Even if you gave me all the time in the world, I can't figure out how to add up infinitely many things without a trick. So here's the trick. We examine the partial sum, or really the partial sums. So S1 here is just 1. Partial sums of the series. And I might as well put the series in sigma notation here. This is sigma k equals 0 to infinity. I guess I should call this S0, shouldn't I? Of 1/2 to the k. That's what this is, right? 1/2 to the 0 plus 1/2 to the 1 plus 1/2 squared plus 1/2 cubed plus 1/2 to the 4 and so on. So the 0th partial sum, the sum you get if you plug in, if you were to go from 0 to 0, it's just 1/2 to the 0, that would be 1. I'll even write it out here like this. This is sigma from k equals 0 to 0, 1/2 to the k. That's just 1/2 to the 0, which is 1. But really, I'm just saying it's the first term. S1 would be sigma k from 0 to 1 of 1/2 to the k, which is 1/2 to the 0 plus 1/2 to the 1, which is 1 plus 1/2, or 3/2. S2 would be sigma k from 0 to 2 of 1/2 to the k. I'm not gonna write this thing. I'm gonna write it's just 1 plus 1/2 plus 1/4. And that's 3/2 plus 1/4, which is was it 5/4? So 3/2 would be 2 6/4. 3/2 or 6/4 plus 1/4. Oh no, I'm sorry, 7/4. Yeah. S3 sum k equals 0 to 3 of 1/2 to the k, which is 1 plus 1/2 plus 1/4 plus 1/8. And I know that these first three add up to 7/4. If I multiply that by 2/2, I get 14/4. Sorry, 14/8 plus 1/8 is 15/8. And we can keep going like this. Maybe I'll do one more, and then I'll ask if you see a pattern. So S4 is the sum from k equals 0 to 4 of 1/2 to the k, which is 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. And I know that the first four terms add up to 15/8. If I multiply that by 2/2, I get 30/16. So this is 31/16. Does anybody notice a pattern in these?
Each one is 1 below 2.
Yeah. So 3/2 is 4 minus 1/2. 7/2 is 8 minus 1/2. 15/2 is 6 over. I'll write it. 3/2. This is 4 minus 1/2, or 2 squared minus 1/2 to the 1. 7/2 is 7/4 is 8 minus 1/4, which is 2 cubed minus 1/2 squared. 15/8 is 16 minus 1/8, which is 2 to the 4 minus 1/2 to the 3. And 31/16 would be 2 to the 5 minus 1/2 to the 4. So it looks like Sn, like here where n is 4, is 2 to the n plus 1 minus 1 divided by 2 to the n. Pretty cool, right? So just from seeing the pattern, and then I can do some algebra with this. This is 2 to the n plus 1 over 2 to the n minus 1 over 2 to the n. And 2 to the n plus 1 over 2 to the n, that's 2. Right? The power up here is 1 greater. And this, you divide like bases, subtract the powers, right? N plus 1 minus n is 1. And then minus 1 over 2 to the n is the same as 1/2 to the n. And remember what I told you yesterday. If r is smaller than 1, then r to the n goes to 0 as n goes to infinity. So we know if, and when I say smaller, I mean smaller in absolute value. R is less than 1 in absolute value, then r to the n goes to 0 as n goes to infinity. Therefore, as n goes to infinity, Sn, this thing, which is 2 minus 1/2 to the n, the 2 is just a 2, but 1/2 to the n looks like r to the n. So this thing is going to go to 2 minus 0, or just 2. And this leads me to one of the worst math jokes of all time. An infinite number of mathematicians walk into a bar. The first mathematician orders a beer. The second mathematician orders half a beer. The third mathematician orders a quarter of a beer, and so on. The bartender says, "God, I hate you guys," and just pours 2 beers. I know it's not even funny. I just can't help telling it when I teach this. It sits in some part of my brain that math teachers have to tell bad jokes. The big deal is we found a nice formula for the nth partial sum. So we can now say that the full infinite series from k equals 1 to infinity of 1/2 to the k is actually equal to 2. Because as you let the series get longer and longer and longer, it gets closer and closer and closer to 2. Imagine you plug in 1,000 for n here. That would be 1 plus 1/2 plus 1/4 plus blah, 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 all the way up to 1/2 to the 1,000. It's a sum with 1,000 terms in it. It would be equal to 2 minus 1/2 to the 1,000. So this part is almost 0. And as n gets bigger and bigger and bigger, as your sum gets longer and longer and longer, its value gets closer and closer and closer and closer to 2. This is what it means to say that an infinite series has a value. Some infinite series don't have values. Right? 1 plus 1 plus 1 infinitely many times. The sum sigma k from 1 to infinity of 1 definitely doesn't have a value. The only value you could possibly call it is infinity. You may have heard the joke that 1 plus 2 plus 3 plus 4 plus 5 on and on forever is -1/12. First, that's bullshit. It's not. It's not. It comes from something called analytic continuation of something else called the Riemann zeta function. But that would be another example of a divergent sum, a sum that does not have a finite value. Okay. I'm not going to go too deep into what infinite series are, but I'll say this. Infinite series, like S equals sigma k from 1 to infinity of AK, can do one of two things. One, they can converge, meaning have a finite value. Or they can diverge, which is to fail to have a finite value. What it means to converge is that the sequence of partial sums Sn goes to some definite number. As n goes to infinity, And what it means to diverge is for that to not happen. And there's lots of ways for that to not happen. In Calc 2, we'll explore in great detail conditions that are both necessary and sufficient for a sum like this to converge. And we'll also have tests that can tell us under certain conditions a series for sure diverges. And then there will still be many, many, many more series that are hard to work with. But you will explore this in some detail in Calc 2. There is, however, one family of sums that I can teach you everything about here, and it's the very last bit of content for this course, and those are geometric sums. Sums where the thing you're adding up look like 1/2 to the n, or somehow similar to that. These are called geometric series, and they're a series of the form, call it S equals sigma k from, I'm going to go 0 to infinity, a times r to the k. Here a and r are constants. So these things look like a plus ar plus a times r squared plus a times r cubed, and so on and on and on forever. I'm going to show you how to come up with a formula for the nth partial sum of this series. So we'll be able to work this out in general. It's not too bad. This would be, well, this thing, right? This thing, but stopping. So that's a plus a times r plus a times r squared plus a times r cubed plus all the way out. All right, the second to last and the last term. The second to last term here would be a times r to the n minus 1. And the very last term would be a times r to the n. You might think, oh, well, just from this, I can like let n go to infinity and say this last term here has to go to 0, so I get this other stuff. But then you realize that this actually has an n in it also. And what's worse, the sum gets longer and longer as n goes to infinity. So I can't really say what's going on in the dot, dot, dots. So rather than approaching this directly, what I'm going to do is a very sneaky thing. I'm going to multiply on both sides by 1 minus r. And that way I will be able to simplify and get a nice closed formula without any dot, dot, dots for the Sn. So 1 minus r times Sn is 1 minus r times this thing above. I can distribute the 1 and distribute the r. When I distribute the 1, I just get this thing back. And then when I distribute the minus r, I'll get minus r times a, which is minus ar, minus r times ar, which is minus ar squared, minus r times r squared, which is ar cubed, and so on, until I get down to the term just before the a times r to the n plus 1 in here, which is a times r to the n minus 2. R times a times r to the n minus 2 would be minus a r to the n minus 1. R times a r to the n minus 1 is minus a r to the n. And then minus r times a r to the n is minus a r to the n plus 1. And you can see, based on how I've sort of suggestively lined these up, these cancel. These cancel. These cancel. Everything cancels except the very first term and the very last term. Divide through by 1 minus r. So what we've got here right now is, all right, it's therefore 1 minus r times Sn is equal to this. So this implies that Sn is equal to a minus ar to the n plus 1 over 1 minus r. That's it. There's one more thing we could write here. I guess this is a time, or a minus a r times r to the n divided by 1 minus r. I am assuming here that r is not equal to 1. But if r is equal to 1, this is pretty boring, right? This is just a plus a plus a plus a plus a n times. So the partial sum would be na, or I guess n plus 1 times a, because we're starting at 0. And what's more, if we know that the absolute value of r is less than 1, then we know the r to the n piece will go to 0 as n goes to infinity. So as n goes to infinity, Sn will go to this piece, but with the r to the n swapped by 0. So that would be a minus ar times 0 over 1 minus r. And ar times 0 is 0. So that's a over 1 minus r. And this is a famous result on geometric series that was known even to people in ancient India, like around the writing of the Mahabharata, a very, very long time ago. This was known, preceding ancient Greece. This was known. Pretty cool, right? I'm going to show you that the problem we did earlier with the 1/2 can be couched in terms of this formula, and that so can lots of others. So this formula, let me state the results. So here we've discovered that if absolute r is less than 1, then signal k from 0 to infinity, a times r to the k is equal to a over 1 minus r. This is the famous result on geometric series. And this is the last thing I'm going to ask you to remember for me this semester. So this object right here is called a geometric series. It's a series or an infinite sum whose terms are geometric, come from a geometric sequence. So we can use this to find sigma k from 0 to infinity, 1/2 to the k, the thing we played with earlier. This looks like this. A here is 1. R here is 1/2. This is geometric. So geometric series with A equal to 1 and R equal to 1/2. So this should be equal to, without any of the work, just using the formula, should be equal to A over 1 minus R. 1 over 1 minus 1/2. Well, 1 minus 1/2 is 1/2, so the downstairs is 1/2. And then when you divide 1 by 1/2, that's the same as multiplying 1 by 2 over 1, so there's your 2. Just like we found before. So infinite number of mathematicians bar 2 beers, right? We can do other stuff too. So suppose I want to find sigma k from 0 to infinity. I don't know, it sounds like fun to you guys. How about negative 2/3 to the n? This is also geometric. This is the geometric series. Again, here a is equal to 1. This time r is equal to negative 2/3. Now you need to stop and check. Is the absolute value of r less than 1? Here it was. Absolute value of r is absolute value of 1/2 is 1/2 is less than 1, because we need that to be true in order to use our theorem. Here again, it's true. The absolute value of r is the absolute value of negative 2/3, which is positive 2/3, which is indeed less than 1. So I can use my theorem, my formula, saying sigma k from 0 to infinity, negative 2/3 to the k should be a, which is 1, over 1 minus r, which is negative 2/3. Now that downstairs, we clean that up. That's 1 over 1 plus 2/3. 1 is 3/3, so that's 5/3. This would be 3/5. The very last thing I'm going to do for you here. So there's enough use of that formula as it is. There's plenty of other things one can do with it. But the very last thing I'm going to do for you here is investigate the function. And now I'm using function in the sense of a real variable function. I'll call it f of x, but I'm going to define it as an infinite series. Oops, sorry, x to the k. This looks an awful lot like the sort of stuff you saw my differential equations kids playing with. Theirs were a little more complicated. This still looks a lot like this, except it's got a variable in it. It's still a geometric series. Here, r is the variable x. So as long as the absolute value of r, which is the absolute value of x, is smaller than 1, this thing should be equal to a, which is again 1, divided by 1 minus r, which is x. Oh shit, that's a rational function. That's one of those functions we learned how to graph earlier. It is. It really is. It's a function. It's a rational function. It has a vertical asymptote at x equals 1. And its domain is just negative 1 to 1, because absolute x less than 1 is the same as saying negative 1 is less than x is less than 1. The graph of this function looks like this. It's not an exponential, it's a rational function. But it has that kind of shape. But what's really cool about this thing is that you can interpret it as an infinite polynomial. 1 plus x squared plus x cubed plus x to the 4th, going on and on and on forever. This is going to be a huge deal down the line, way down the line, so don't panic about it yet, but way down the line in your calculus classes, this is going to be a big fucking deal. The fact that you can define functions as infinite series. This one happens to be geometric, so we've got a formula for how to sum geometric series. That formula gives us a rational function. We know what that looks like. All right, if I wanted to draw the whole graph of that 1 over 1 minus x, it would have a horizontal asymptote, y equals 0. It would have another branch down here that looks like this. All right, those are functions that we've studied. Very last thing I'm going to do here, I'll show you what this looks like in Desmos. there's that function. It's the same graph I just drew for you. I'm going to pay close attention to the interval from -1 to 1, which is like here. Maybe I'll draw a second version of it. So I claim that this blue portion is the interesting part for us. Let's look. I'm going to turn this off so I can hide it from you. All right, you ready? Watch the green. Looks an awful lot like the blue. And the more terms I give it, the more it'll look like the blue. Pretty much everywhere between -1 and 1, I can't tell a difference between the blue and the green. Only over here, as we get close to the edge of the interval from -1 to 1, can I see any difference between the blue and the green. Now, outside the interval -1 to 1, these are totally different animals, right? Because this infinite series only converges if the x values you plug in satisfy the rule from the formula. If you have infinitely many terms, you will actually just get this. But of course, I can't type infinitely many terms into Desmos, so I'm limited. So that's it, guys. That's pre-calculus. That's everything you need except the trigonometry to whoop some massive ass in calculus. I'm ready to let you go. Do you have any questions for me before I do that? Remember, your take-home test is going to be out today. That's your last midterm. And then your final exam is on Monday. There will be one last quiz coming up in WebAssign and a short homework on sequences and series.
For the take-home test, is there a time limit or do we just download it, print it out, and then give it to you by Monday?
That's it. Just download it, print it, and then hand it in on Monday. No time limit. The rule is that the only resources you're allowed are your notes.
Where do we download it?
I'm going to post it to Canvas today.
Oh, okay. All right. So it's not up
I
yet.
haven't posted it yet, but I will be posting it after class.
Got it.
Are you having office hours today?
I am going to have office hours today, although I might be a little bit distracted because I'm about to be on baby duty. But yeah, I'll be there. I'll be there. I can talk. I can write small amounts, but mostly I'll be there to talk. Anything else?
And you'll just email me once you hear from the director?
Yeah, I'll have to kind of ask her. I'm sure she's going to say yes. And then you and I will talk to set up an alternate date.
Okay, sounds good.
Alrighty, guys, I'm gonna go ahead and end our meeting. It's been a wonderful semester. Make sure you put in the work here in these last few days, get comfy with that matrix stuff, get comfy with the sequence stuff, and everything will go beautifully from here on out. If there's anything I can do to help any of you, don't be shy about asking. I know I'm a little bit behind on my email. If you're waiting for a response, I'll just beg your patience. It's a busy time of the term. And I wish you all the best in the future. If you're interested in the math team ever, come talk to me. I'm here. You've got my contact info. You know how to do that. If you want to take Calc 1 or Calc 2 with me in the future, I'd love to see you there. If you have questions about calculus professors or anything mathematics related in the future, I'm always available. So take care, guys. I'll see you for the final on Monday, right? 8, 9, your final. Let's get that super duper clear before we leave. Your final. Yeah, 8, 9, and I believe that is Monday, right? Yes. Okay, so everybody except Ainsley. I'll see you guys on Monday for the final. Ainsley, I will get back to your email here in just the next few minutes. Bye, guys.